growth of being challenged by one of our members, Brent Davis, to take a harder look at solar. I'm kind of a skeptic of solar energy, not as a great weapon in our march towards renewable and sustainable, because solar energy is very good resource in many areas, but I have been skeptical of its role in Cordova. But this spring, again, Brent had challenged me to take a harder look at solar, and I knew the technology was improving, but we had a great solar energy workshop in Anchorage in May, June, somewhere in that range. And it actually collected a whole bunch of projects around the state of Alaska. And I saw some really surprising and encouraging advances, and I actually dispelled some of my misconceptions about some of the challenges with solar. So when you roll that all together, well, I'll show you. So this is some solar panels at University of Alaska Fairbanks.
You want me to hit the lights?
Yes, please. And, so this actually looks kind of discouraging, but the good news is this is just right after a snowstorm. And if you'd stuck around for a couple more hours, you would have seen all of this snow slip off by itself. And you would have seen the sun heating all this snow in front and reflecting onto the solar panels. And they actually got some really good solar gain even in winter conditions here. So here's some things about solar energy in Alaska that I gleaned from the conference. And I have a lot of the, I grabbed quite a few of the presentations, and I brought copies of them here, and I'll just keep a binder of them at my office, but I'll also show you a link at the end to many of these presentations for some background information for you. And it's a lot of the source material for my presentation here. So solar panels perform really well at low temperatures. So that's a good thing for Alaska. You actually get a better output than published output in cold weather. We have a high albedo in Alaska, and albedo is just reflection off of surfaces to give you extra solar output. So snow and water help with that. We have exceptionally clean air in Alaska, so there isn't a lot of what solar would do, but there's very little interference with it. Solar panels, one of the things I love is simple when it comes to energy solutions. And a huge advantage of solar is there's no moving parts, very low operations and maintenance. That's a big deal for Alaska, where maintenance, cost, and labor is expensive. This is a big one, especially for Cordova. The peak solar gain in Alaska is in March and April. So it's kind of a little counterintuitive, but Alaska is farthest from the sun in the summer and closest in the winter. So kind of where those two solar energy paths cross is in March and April. In Cordova, we are often very close to 100% diesel in those months. So that really caught my attention. Snow reflection helps a lot, but shading hurts. And I'll talk a little bit about different types of installations and why trees and mountains can impact a solar installation. Snow load and wind can be managed and mitigated a lot better than I anticipated, especially passively. It turns out that snow will often blow off or just melt off the panels, even at far northern temperatures. And of course here in coastal Alaska we have much milder temperatures. The cost on solar panels keep dropping. You'll hear me bring that up several times. However, installation is much more complex than you would think. The technology, the physical installation, the electrical codes, the insurance and warranty pieces are quite a bit more complex than you would think. And of course, especially in Alaska, simpler is better. So here's some of what technology has done, and you can go on the internet and find myriad numbers, but these are just kind of comparative numbers for what's happened in the last 5 years with solar. You can see on the residential side, cost had dropped in half. Same with commercial, same, even more dramatic in the utility circles, probably because you get an economy of scale. The more panels you buy, the more panels you put on a given location, the better the cost becomes. So $1.80 a watt is pretty compelling. And just to give some comparisons with some Cordova projects, I went back to kind of see how solar compared. Power Creek was built in 2002 at a cost of $3.83 a watt, and the project has a 30% capacity factor. That means if you build a 6 megawatt project, on average, you're going to get 30% of that, or about 1.8 megawatts. Humpback Creek, $18.40 a watt. Extremely high cost. It's a small project, remote project. This was actually a rebuild project, and it had a lot of really negative cost drivers involved. It also has a 30% capacity factor. So for the 1,200 watt project, we averaged about a 1,200 kilowatt project, we averaged about a 400 kilowatt output. The Kodiak Wind project, believe it or not, I worked at Kodiak Electric before. I know the manager pretty well. So I got kind of the inside scoop on the real cost of that project, what the whole cost was, and not just the kilowatt hour cost, which includes subsidies, grants, and other things. And it turns out that Kodiak Wind is almost exactly on par with Humpback Creek. This was at a point in Humpback Creek where I was trying to decide whether we wanted to continue with the reconstruction of it. It got pretty ugly for a while, and I was encouraged that it was pretty much on par with Wind. Recent diesel installation by Cordova Electric in 2007 was about $1.25 a watt. You can see why diesel is so compelling on the one hand in comparison to other technologies, but of course you pay for fuel forever. And the interesting thing to me is, look at this. Community scale solar is getting almost down to the cost of diesel, which has historically been one of the cheapest installed costs. And of course your energy cost for sun, pretty favorable compared to diesel cost. So the solar capacity, solar installation cost, you can see on a utility scale, this is 2 years ago, is as low as $1.80 a watt. The capacity factor isn't nearly as good, 10% capacity factor. Yeah?
Just a quick question on the diesel. That's just installation though.
That is just the
figure
installation.
fuel.
It doesn't include the fuel at all.
Okay.
So that's the big trade-off.
Okay.
This fuel for Power Creek cost us $100 a year. That's what our water permit cost. Yeah, Andy?
And Clay, do you assume on the diesel that it's 100% capacity factor?
It is 100% capacity factor, so as long as you've got fuel in the tank, our diesels are pretty much 99% available.
Okay.
We take them down for maintenance, but then we have another one available for backup. So, and please do just jump in with questions as we go. That's a great way to. This is fairly informal, and just jump in. So, any questions so far? Other questions? Okay. This is really surprising to me. This is a resource map of the U.S. that kind of shows what you would expect. Very favorable in the Southwest. But here's another one. Germany has the highest solar penetration as far as installed solar on the planet, I believe. Look at that resource map compared to Alaska. Not too dissimilar. But then, if you look at solar penetration on a flat plate that's just a solar panel put in one place facing south, this is pretty amazing. And this graphic here, I bet, showed up in a dozen different presentations. So the data came in, and I think people were just as alarmed and excited by it as I am. Here's Hawaii, and there's Alaska. So a little counterintuitive and seasonal, of course, but some of the highest solar opportunities actually in northern and western Alaska. That has to do partly with snow and reflectivity and also cloud cover. So here's some basic solar systems. And I'll show you the passive, or what I call just the thermal solar on this side. And this is just basically converting heat to heat. And really that isn't a conversion, it's just harnessing solar energy, which is thermal energy, and collecting it and then distributing it into a home heating system. So this is really the best solar opportunity for a couple of reasons. Home heating costs in Alaska are higher than most of all the other energy costs combined. Transportation, electricity tend to be lower than home heating costs. So if you can take solar energy and just harness it as heat and store it and deliver it as heat, that's really the most cost effective. You can get 70 to 80% efficiency out of these vacuum tubes. And even a simple system where basically you pump cold water, say, onto a roof line and let it run down, trickle down some dark colored ceiling or roof panels, metal roof panels, and collect it and store it in a hot tank. Even something that simple can have some amazing high efficiency. And then if you go to a system that's designed again with vacuum, and in a fairly robust system, you can get up to those 75 and 80% efficiencies. What we're mostly going to talk though about is photovoltaic, which is converting solar energy to electricity. That's more in the 10 to 15% efficiency range at your current technology efficiencies. So there's two options basically. In rural Alaska, especially recreational counties and whatnot, this is a typical installation, which is off-grid. It's not tied to the grid. It has some downsides, but it has some upsides. You need some kind of storage so that you can gather and harness your daytime solar and use it in the evenings. But you can use that DC power to directly power DC devices. So you can have DC lighting, you can have DC appliances, use those during the day. In fact, unless you have something that demands AC power, you don't even need this inverter. So this can be fairly simple, fairly inexpensive, and you avoid a lot of complexity when you don't have to start dealing with the electric utility and a grid connection. The charge controller is what helps efficiently charge the battery from your solar panels. So, any questions on that setup? Okay, a little more complicated is tying to an electrical grid. But there's some advantages as well. You don't need your own battery storage. You basically use the grid as your storage. So you can take your solar energy, use what you need of it, bank the rest to the grid, and then get power back from the grid when you need it. So that's kind of a sharing arrangement at the simplest level. Problem is that if you don't have battery storage or some kind of storage at your house, if the grid goes down, you go down. And you can't, even if your solar panel is producing power, you really can't use that because it's being converted. Unless you have a battery and have a way to use some of your own solar, you wouldn't even be able to use your own solar panels. The good news is for Cordova is we don't have very many outages because of our underground power systems. So, it does still require an inverter to convert your DC power into AC power, but you get the full advantage of your inverter. You can size that to your solar array. It requires both AC and DC disconnect switches and whatnot, because now that you're dealing with grid power, you have to protect the grid from your system and your system from the grid. It has to be installed outside where it's accessible, and the power is limited not only by the sun but also by the grid. And maybe I should explain that a little bit now. So if you have in the middle of the day, say 3 kilowatts of power available, and you're only using 1 kilowatt at your home, the grid has to have a demand for power at that time to take, to buy, to give you credit for your power. This is one of the primary challenges in Cordova right now. We spill power a good portion of the time, and if the grid is already spilling renewable energy, that doesn't make it a good place for you to sell your solar power or pay it into the grid as credits so you can get power back when you do need it. So that's one of our challenges, but we have some opportunities along those lines as well. I'll explain. This is a pretty exciting model. It's one that a lot of cooperatives are using, and it has some big advantages. Instead of mounting, say several people in Cordova want to have solar power at their own house. Instead of installing several small individual panels in several locations around town, especially where you may get some tree shading or some mountain shading, or it's not the most attractive location, and it runs into issues of having to install the wiring and everything in your house and meet those codes, have DC wiring in your house, and some of the other issues go with it, as well as, in most cases, a rooftop solar installation isn't the most optimal. A community solar installation says, well, Greg, I want a solar panel, but the reluctant isn't a good place, so we're going to build this community solar installation at a real attractive location. Let's say out at the airport where they just cut all the trees down. You've got this great line of sight to a full southern exposure during the day. You can build one solar panel there, you're close to the grid. Might even be able to share some, say some Alaska Airlines floor space or something, but you can have one optimal place. But each of you, Greg could say, well, I'm gonna own one of those panels out there and have the economy of scale of having one big installation, one big inverter string, and Andrew could buy a panel, Troy could buy a panel, I could buy a panel. So we're each getting kind of a large scale installation where we get the economy of scale, but we all have our panel in an optimal spot, and then we just have one meter that says, okay, and now actually each of these individual panels are starting to come with their own electronics and meters. But we could just say, well, here's the whole output of that thing divided by X amount. So each of us gets credit for the energy our solar panel is producing in an optimal location, closer to that $1.80 a watt cost than that $6 or $7 a watt cost. And then through your cooperative and their extended network, you can hopefully have the most optimal installation. So this is kind of what I'm excited about, and I'll be honest, I'm not real excited about solar yet. I'll talk about that. But I do think that this is a great opportunity to, if the community wants solar, I think this is a good model for this. And that's an actual, these are some actual costs in a solar installation in Indiana. So here, this is right out of the National Rural Electric Cooperative Association, which we're a member of, basically 1,000 co-ops around the country. Co-ops in about 20 states are doing community solar projects now. There's hundreds of them. Our national organization has a great online calculator that you can enter your latitude, your zip code, the size of the bank that you want to do, and they'll pull in the different financing options and everything, and they have design sets that they've got 4 different designs for community solar installations, like engineered drawings for building a solar panel. They've got several different financing models, so there's really deep resources on the cooperative side to help develop these. They're saying cost on the megawatt scale is low as 6 to 12 cents a kilowatt hour, and on the residential 5 to 10 kilowatt scale, which would be more our community size scale, 11 to 20 cents a kilowatt hour. Now remember, these are in optimal location for construction costs are low and financing costs, frankly. So what do some of these things mean for Cordova? What are our opportunities? I mentioned spilling hydro. Now we're lowering the dam here, but this is very often what Power Creek looks like. 60% of the time we're spilling excess energy. And that's the real frustration of our system. The other 40% of the time we're generating a diesel. And if we could just store this energy somehow, it'd look more like 90 to 95% hydro for Power Creek alone, and how Back Creek could take us right over the top to over 100%. So these are actually a lot of solar energy data has been collected around the state of Alaska. And, oh my gosh, tell me. So the one, I can run back over and get it after the presentation. The one great book that I wanted to bring is called the Solar Design Manual for Alaska. And I read the book cover to cover. It takes you start to finish, all the different technologies, things to look for, how to build out in Alaska if you want to. And it has resource data for a lot of communities. So here's a summary. Cordova's like many South Coastal and Aleutian sites, unpromising as a solar water heating location. And you can extend that to solar voltaic. But also, like many of these locations, it does have renewable electricity from a hydroelectric dam, which is an excellent renewable alternative to solar water heating. This is an important number. It's a solar fraction. The federal government, to get the incentives, the tax benefits, the rebates and everything, you have to achieve at least 50% solar fraction. Cordova's not quite there. And you can see there's times when we are again. This is the exciting thing to me, because this is where we really need solar. This is where we are almost always generating with diesel. And that's where a big chunk of the solar energy is produced. But even compared to community like Dillingham, ironically, you get farther west, the solar data is better. Yeah.
So this is just based on the latitude, it's not based on cloud cover versus the airport?
It's based on all the above. It's actually the SNOTEL site collects solar data, and has for years and years. But this includes all that. And this is actually a lot of it's due to cloud cover. You get up to Fairbanks, you get up in like 60s and 70s here. But I'll tell you, I talked to a applications engineer at Eastman several years ago, and he told me that cloud cover takes your efficiency, drops your efficiency by 25%. So if on a perfectly beautiful sunny day you can get 8 kilowatts out of a 10 kilowatt panel at high noon in Cordova in July, if it's cloudy that same day you'd only get 2. So what I was seeing, most of the data I was seeing in this workshop is the panels are now achieving efficiencies of 50% on a cloudy day of what you would get on a sunny day. So that also kind of tips my thinking a little bit towards solar. These are actually pictures of Crater Lake. Somebody asked me if I could answer some questions about Crater Lake tonight. And we'll just tack that on to the end if there's any questions. But these are some fantastic junctions at Crater Lake. Cordova Electric is a cooperative, so you own it if you buy electricity. So we aren't just cost or profit driven, we're value driven. If the community wants a solar project, we will find a way to make it happen and find a way to do it so that the people who want the solar and buy into the solar are the ones who bear the cost. And that's where I think this community model is great. If we want solar in Cordova, we'll find a way to make that happen. But what we're looking for is energy security, and that's both reliability and just security of our energy. Responsibility, mostly that's environmental and public and employee safety. Sustainability, we want to have our energy needs met in the future, and it has to be affordable. We have to be able to pay for it. So how does solar fit into that? Well, some of the challenges are that, I already explained this, renewables, we want renewables to compete with diesel and fossil alternatives. But unfortunately, sometimes renewables compete with each other. The closer you get to 100% renewable, the harder sometimes it is to make that next little piece of renewable that's left. And I explained we spill hydro 60% of the time. Solar is extremely variable. That cloud cover, unfortunately, a cloud can go by and take your solar output from a high output to 20 or 30%, just like that. So that makes it very challenged to manage on an electric system. The more solar you put in your system, the more dramatically that swings around. And power systems, grids, are developed kind of like water systems. You start with very big circuits, and they get smaller and smaller and smaller as they go out. So if you try to put a big energy source out on the end, all the grid is backwards. You're trying to feed into very small wires back onto a big system. We don't have any concerns about that now. We have to install a lot of solar before that becomes a problem. But when you hear about places like Hawaii, the utilities not letting people add solar, that's why. Their whole grid is built backwards, and it literally starts causing outages, and you can't, you don't have enough other energy resources to stabilize those fluctuations in solar. Small solar installations lose the economy of scale. Again, an argument for a community installation. But the larger it gets, the harder it is to integrate. Those nice 6 to 12 cent a kilowatt hour, 1 megawatt plants, we're running right about 2 megawatts right now. Our whole system's at 2 megawatts. So if we had a megawatt solar going during the middle of the day and a cloud goes over, we don't have enough backup. Half of our system would probably go out on an outage. So we can't integrate that much solar into our system yet. Solar energy is somewhat limited because of the cloud cover and then just the seasonality of Alaska. And we really don't have solar experts in Alaska. I'm just giving you kind of a high-level brush. I have access to a lot of resources, but I'm not by any means a solar expert. So some of the opportunities on the good side, these are all Crater Lake flower pictures, by the way. Solar peaks when we need it most, March and April. We're very often, we have been 97% diesel in April, in a cold April. Community solar could be a very optimal solution. It doesn't mean that it's an optimal resource. It means that if we want to optimize solar, here's how I feel. I'm very skeptical about solar. I don't think it pencils out economically, but when you first adopt the technology, sometimes that's the case. But if we're going to try solar in Cordova, I want it to have the best chance of being successful. I want to give it the best run we can. First of all, we'll get more out of the investment, and second of all, we might find that it's more successful than we hoped. And that puts us in a place of doing more. Solar continues to decline in cost. It's been a very sharp drop recently, very encouraging, and at the same time, the efficiency keeps improving. So it's becoming a more and more feasible technology even for us in Alaska. This is an important one. We're looking at hydro storage, and this is kind of a tie to Crater Lake, but once you have a grid-scale battery, and hydroelectric would be a great battery, all the other intermittent renewables become a lot more feasible. So if all of a sudden now you can have this hydro running in the background, delivering power out of stored hydro, and the sun comes out, you can close down your hydro valves and store that water and use your solar. And then when the sun goes down at night, you can start drying out your hydro again. So you can play those renewables against each other so they start complementing each other instead of competing with each other. And that's why storage is so important on our system. We've looked at battery storage, we've looked at flywheels, we've looked at short-term and long-term storage. It's really the next thing that's going to really help improve our overall system efficiency. The other thing that happens is you can play hydro against storage generators to get more efficiency on those things. Solar is low maintenance. I love low maintenance. Keeping operating costs down in a small system is really critical, and solar is a great opportunity here. And solar is visible. You can see the solar panels, and it does a lot for the psyche of the community. It's one of the reasons why wind and solar are so popular. You can see the panels, you can see the windmill spinning, and it doesn't just feel good, it is good, but it helps kind of propel our mindset, I guess. So some of the takeaways: timing is everything. I'm not a big fan of solar right now, and that's because it gets so much better if, say, we have some hydro storage on the system 2 or 3 years from now. Solar's going to have improved quite a bit during that time frame, and now we have a complementary renewable resource that makes it better. CEC has some footwork to do. We need to do all the painful, bureaucratic work to make it very simple for you to inject solar into the system if you want to, whether it's through a community solar program or through solar panel. And it's not fun work because there's other things to do. It's like, okay, I got to bring to this administrative thing, but we need to do that. Not just for solar, but for wind or other opportunities. Partnering is always a cost-effective approach. There's strength in numbers and the economy of scale. It's why grids work. We can all probably go out and find 100 small hydro resources and develop 100 micro hydros. You're not going to get anywhere the kind of efficiency or reliability as you are at one utility scale hydro plant. And that's a great thing about a co-op. We all own part of that hydro plant. There are many, many resources, and I've laid a lot of those out here. National Renewable Energy Labs. Most importantly, the Alaska Center for Energy and Power that sponsored this workshop, and the National Rural Electric Cooperative Association. A lot of them have done a lot of research, and a lot of them have done a lot of research in Alaska, so we don't have to reinvent the wheel. Measuring solar can be very expensive, and actually what I'm trying to say here is don't go out and spend $3,000 putting up light meters if you could put $3,000 putting up a solar panel. I mean, why not just harness the energy and measure while you're collecting it? Especially since there hasn't been a lot of solar development in coastal Alaska. And measuring the resource answers the question, how much is there? So why not generate some energy while you're measuring? CEC needs to move from kind of monitoring solar. I think we're at the point where we need to start measuring. Now, I was reminded that we have the Snowtail site, so we need to at least grab that data set, look at it, and see the totals. And then my question for you is, are you interested in solar energy or a solar energy project in Cordova? And what do you think of the community solar project? And this last little slide is ACEP again, Alaska Center for Energy and Power. They've done a lot of work in Cordova. They did a big study for us to help us improve our diesel fuel efficiency at our plant and dispatch hydro to heat our diesels and look at a dispatchable electric boiler for the community swimming pool. They hosted this workshop, and all these publications that are on the table, plus others, are available on their website here. So I think this is going to be posted on the Science Center's website, or this video.
Yep.
So that's just acep.uaf.edu/publications/conferences-presentations.aspx. And these are some rhododendrons of the Crater Lake. So questions? Yeah.
You talked about the spillover with our hydro, and I don't know, I've watched a couple shows where they were talking about the excess solar in Hawaii, or, you know, that they were having trouble utilizing all the solar there. And there was a one gentleman that invented Tetris, and he had his own solar system for his ranch. He was producing more solar than he could use, and he was actually using excess electricity to generate hydrogen for his farm machinery. Would hydrogen be an option as a storage for our hydro that we're having to spill?
I'll say maybe, because I got real excited about hydrogen about 10 years ago, and I researched it real heavily. And the problem with hydrogen, the problem with electric energy, is storage. Electricity is a light speed commodity, and the thing about grids is it exactly matches how much is needed with exactly how much is produced. And if you produce more than you need, or you need more than you can produce, there's an outage going to happen somewhere. But hydrogen is the smallest molecule. It can literally move through almost any medium. In other words, migrate through it, literally pass through metal and everything. And 10 years ago, and I don't think the technology has improved much, it cost 10 times as much just to store hydrogen as it cost for natural gas delivered. So now, another kind of little side path that's really interesting to me is producing liquid ammonia from electricity. So the 1917 Nobel Prize was using electricity to gather free nitrogen from the air, crack water into hydrogen, and then making NH3 ammonia, anhydrous ammonia out of it. It turns out ammonia has half the energy density of diesel fuel, which is actually very high. And if you use a catalytic converter, you return, when you combust ammonia, it returns to free nitrogen, free water vapor, and free hydrogen. So it's a very clean cycle. And but the problem is the manufacturing scale. So hydrogen is improving. It's feasible in some cases if you use it very quickly, but if you try to store big, huge volumes of it and ship it from like this week to next week, it gets really hard to store it. So, but there's some cool stuff. And they superheat metals and hydrate them, and they can get clear up to the densities of liquid hydrogen that way. But it takes a tremendous amount of energy to store it.
But when you were saying that we're spilling hydro, are you saying that we're creating more electricity than we can use, or that
if we were running that water through a turbine instead of running it over the dam, we would have a lot of excess electricity. And ideally we would, and we don't always know when that's going to happen, and we don't know when people are going to use electricity. So what happens sometimes is the processors in the community will be using 8 megawatts of power during the day, and we are running a diesel because that's more than both of our hydros combined, about 9 megawatts. But then by that night, when the town shuts down, the system load will drop down to 6 or 7 megawatts. Then we're spilling hydro again. So just in that one day's time, we go from too much hydro to not enough and back. And then a lot of it's seasonal. We spill most of our hydro between June and October, most years. But this year was crazy. January, all the rain, we had 7 to 8 megawatts of hydro available for most of the month. And the town was using 2 megawatts. It just makes me want to cry because all our snow's melting and going down the river. Then in July and August when we needed it, there's no snow. But we are working on tools, we as a co-op are working on tools again to at least use that electricity to heat our own diesel generators, for instance. 4% of the diesel we used last year was to keep our diesel generators warm, mostly in the summer when we're not running them. Because you have to keep them warm enough to quick start them, 130 degrees. But if one of them isn't running and circulating that heat to the others, when we're 100% hydro, we're actually running a diesel boiler to heat those. Well, meanwhile, we're spilling hydro a lot of the time, so that's when thermal storage gets real attractive. We can use an electric boiler to heat a big tank of water in for 5 or 6 hours real intensively. And then when we switch back to diesel during the day, we can circulate that hot water through our diesels and keep them warm. Or if we switch to 100% hydro, we could switch to that heat. So we can cut our diesel use on our heating, same with the swimming pool. Since that's over 80 degrees, even in the summer, there's quite a bit of diesel that gets used. Greenhouses, LED lighting. Also the tools, our automation system knows when we're 100% hydro. We've been watching electric metering technology is advancing leaps and bounds to where you can have little displays inside your house or whatever that shows you. We're getting to the point that we can not only signal you, the members, owners of the property, when we're 100% hydro, we can actually talk to your devices. So if you're not opening your refrigerator between midnight and 6 a.m., we can be going through, for instance, with the smart devices that are starting to come out of the market, our automation system can cycle through town turning on refrigerators, starting washing machines or dryers, or charging electric vehicles at night, and dispatching that hydro to you when it's, frankly, when all our costs are fixed. We don't need any more employees or it doesn't cost us any more to produce 6 megawatts of hydro than it does to produce 4 megawatts. So we actually have an interruptible rate in place right now for a 7.5 cent hydro. That was meant to be half the cost of diesel. If in our new lower cost of diesel, that'd be more like 3 to 4 cent hydro. And that's available right now in our tariff. So if any of you have a need for power and you don't care when we turn it off and on, we have that low cost. And that helps everybody because that extra revenue helps spread across our costs and keep our power rates down. So what do you think about solar? Or is any of this helpful? Or?
Just one quick, and this isn't even an important question. I was watching the greatest show the other night about these rovers on Mars that were crawling all around Mars. And they've been up there for like 10 years, you know. And they were totally run by solar power. Totally. I mean, for 10 years these things were running around up there. But they got so much dust that they were down to like 90% efficiency. I mean, 10% efficiency. 90% of their solar power was gone due to dirt on their solar panels. And is that a big concern? I mean, if a volcano goes off or just dirt in the air, like we get these heck of a dust flows down the Copper River, I mean, is that any big deal? Or
I don't know. I know spruce pollen has been an issue. At that conference, they said that they'd had problems with spruce pollen.
Oh, yeah.
And I'm not sure if that's because it's sticky and it sticks to the panels, but they have to go out and clean the panels in the spring.
I would think going out there with a squeegee and a roll of paper towels would be a whole heck of a lot of work. You know?
I'd say it's probably a problem until it rains again.
Yeah, there is that. Yeah.
We see the other cycle spring. It's amazing how they said all that snow in the very first picture, it actually shined through and hit the panels and melted the snow from the back. They didn't have any extra heat. This is Fairbanks. He said it was like 15 below or something like that. So that was really impressive to me that they self-shed in those cold temperatures. It tells me they would shed easy with cold running, or west. So, especially vertical. Oh, the other thing, I didn't mention some of the details, but it's in Alaska basically 90% in the winter, 60% during the summer. If you just move them once, you gain almost all the efficiency there is to be gained. You can gain a little bit of efficiency by motorizing them and having them track the sun and everything, but you introduce so much maintenance and so much complexity to working parts that really they say the best bet is to please have fixed panels and just have them so they can easily be moved once a year or twice a year.
Has there been any study about wind power generation in the Cordova area?
Yeah,
As opposed to
and
solar?
Native Village EX, so CEC purchased some wind anemometers, some wind meters, and we partnered with Native Village EX to measure wind in several locations. Wind is measured on a scale of 1 to 7, and 4 is kind of marginal. 4, class 4 wind is where it starts becoming feasible. And we found class 4 wind out on Point Whiteshed, which I kind of expect to have nice smooth air coming off the land there, they call it air coming off the ocean. And you have kind of a smooth ridge, and those laminar lines of wind get concentrated as they go to the top of the ridge. You get some pretty good wind there. But it's very inconsistent. Believe it or not, we get high winds and very low winds quite often. I suspect there's better wind resources in Cordova. It's just finding them. There's so many little microclimates. I was just up Nelson Bay last weekend. It was sunny up there. It was raining in Cordova. So I'm sure there's better wind resources. It just takes some back to find them. Same thing with wind. The technology is really improving. They just had another big step where they're getting the same power that they used to have. Huge turbines there. They're almost half the size, around half the wingspan, and they're getting the same power output. So it keeps getting better, and we can just get storage. That's why Kodiak and wind is so attractive, why they're setting all kinds of records for wind penetration. They've got a 20 megawatt hydro project full of water, and they've got 9 megawatts of wind. 9 megawatts down the wind. And so they use the wind when it blows, and they use the water when it doesn't. And they're at 99.8% renewable this year. So we're at 75. Yeah.
One of the issues is gonna be hooking up to the grid, right? I mean, that can be a huge expense depending on where you locate it. If we did have a solar project out at the airport, can you hook up to the grid directly from there? I'm assuming there's power lines running from town out to the airport.
Yeah, we have power lines. And the other thing about the airport area is there's very few other underground utilities or anything. So even, I think I looked once at extending power down Gavin Lake to that crossroad, back up to the road and back. It's like 6 miles of underground line. It's about what it cost you to do 7 blocks in the city, just because there's nothing else in the way. Yeah, man.
Do you know if the data that you showed in the beginning, the feasibility of, or it was showing our solar possibilities for Cordova, is that for town or is that for the airport area?
Oh,
Where they take weather data?
That weather data?
It was that one right there. Yeah.
It did say where these were gathered. I don't recall exactly where that was.
So I think our main weather data is at the airport.
It is, but
So
it
that would-
could have been Snowtail, but I was surprised by where it was NREL, I think, that actually got this data. And I don't know how. And I left that book over at the office. So, and I also have some information on where to order those. And those are, I just have one that if you want to check it out or flip through it, you can stop by the office. They're available through the Cooperative Extension service for $15. But there are even solar, there's microclimates. Sunny Bay. I've been out to Oswald Bay and seen Cordova Wireless's array out there. I was shocked at how much power output they were getting. I looked at the ratings on it. They were producing like 80 or 90% of their ratings. And it was fairly off-season. I want to say it was March or October or something. And they've had really, Paul said they had good luck with their solar panel out there in terms of maintenance and stuff. So, unfortunately, I don't think they don't log how much they produce seasonally and stuff. I'd really like to see that data set. In fact, that would be kind of aligning for me to just go and put some data in on it and start keeping track. Yeah.
So we were mentioning about water storage, and you wanted to talk about Crater Lake. So I was just curious to know what's going on with that project.
So we, and I had a different PowerPoint presentation for that, so.
Oh,
But Crater Lake is, I mean, not here, but we could, I'm just hinting that we could do that. Crater Lake, we're in the midst of a feasibility study now. Like, we did an internal study, and they're about 90%, well, about 80% there now. In fact, I have a teleconference Thursday morning. Crater Lake could provide 10 to 15% of the community's electricity in our current use, and it could provide as much as 100% of the community's water supply. So the idea is that it's at 1,600 feet of elevation, and you can, it's a glacial cirque, so it's nice hard glacial rock all the way across, and then there's about a 25 to 30 foot deep cleft in the rock that the outflow goes, and then it drops 1,600 feet down to Orchid Nature Lodge. If you filled that gap with concrete so that you could raise the lake as much as 25 feet, if you put the pipe low enough that you could lower the lake as much as 12 feet, you could have active storage of almost 2/3 of the lake's total inflow and outflow in a year. And that'd be on the order of 300 to 400 million gallons of water. That's close to what the city uses in a year. And it's not a huge energy project. It'd be 2 to 3 million kilowatt hours. But the huge advantage to storage is you can use it when you need it, and you can use as much as you want. So one of the things that kills us on our diesel efficiency is we get into scenarios where we have to run 2 of our diesels at 60 or 65% load because it's too much load for one diesel by itself, but it's not enough load to load them up to where they're real efficient. The best way to get efficiency out of a diesel is to run it at 90 to 95% load. So we average 14 kilowatt hours a gallon on our diesel, on our electricity, which is pretty good. But with our quality of equipment, we could be getting 15.5 to 16 kilowatt hours per gallon. So if you had Crater Lake there, and you ran one diesel, and you have stored hydro making up the difference, then you can run that diesel in that really sweet spot. And it's just as the loads go up and down, you fluctuate your hydro to keep that diesel fixed right at that sweet spot. So you can almost get, I estimated we could get as much as 500,000 kilowatt hours, almost 500,000 kilowatt hours just in diesel fuel efficiency out of Crater Lake. And then we spill 500, we have to deflect 500 kilowatts of our grid's capacity to control system frequency. If Crater Lake helped with that a little bit, and then flywheels or batteries to make up that difference, we can get an additional 500 kilowatts out of Power Grid. So that's just like, that's almost the size of Crater Lake as well. So stored energy is really important, and it's what makes the other renewables, tidal, wind, solar, more attractive. So the concerns with Crater Lake, of course, it's a very popular recreational site. I mean, I've spent quite a bit of time there the last 3 years, and it's a beautiful lake, and flooding it or inundating a lot of that is definitely going to change the way it looks.
And these snorkels to see those flowers?
Exactly. So that's the trade-offs, what trade-offs.
Clay, I heard you say, mention a few different ways to store potential energy. One is impounding, when you mentioned thermal, one was solid state ammonia synthesis. So what's CEC's ability to do a comparison of the costs and potentials for implementing those different technologies in those times when we have excess hydro and you want to be able to take advantage of it, but not right now because it's excess, right?
Actually, we've got some great friends. Because we have such an automated system and we've been collecting data for 13 years on every valve position, every diesel cylinder temperature, our whole system has been storing all that massive data. The renewable labs are super excited about that data set because we're a microgrid that it's collected all this data, and it's a hybrid system that has diesel and renewable. So Sandia Labs got about halfway through a model before one of their directors was reassigned, and they literally dropped that exact project, the optimal storage option. And but Berkeley and Lawrence Livermore Labs are both working on a renewable microgrid hybrid optimization modeling program. And they're starting the first phase of that, and we're a partner in the second phase, which is actually putting a model in place. And in this, the model's kind of interesting, it's a little out of the box, but so we had it's called electrotherm, where they take just hot water and convert it to electricity. And they said, what if we installed our equipment here and we're responsible for the operations, maintenance, warranty, and everything? Would you be willing to just buy the electricity from us instead of generating diesel? Like, absolutely. That's what they call the independent power producer. So we'd actually be buying power from someone else, which is a different model, but why not? If they're willing to take the risk and if their equipment works, that hot water is just going to waste. So, but that's part of the answer. We don't have right now, especially as we have a lot of retirements, we don't have the human resources to look at all those complex technologies, and they're all advancing so quickly. It's hard to, you almost have to take a snapshot and put a real intensive effort into comparing them. Fortunately, that's what the national labs do, and they can do it for us.
Are there any members doing interconnect right now at all? Or on the horizon?
Let's see. There's none that I know of, and I don't go looking for it. I mean, I think it's kind of cool. That's the thing about our cooperative model is, as a group, we make our own energy. We're well down the path of being 100% renewable. But especially for something like solar, if we can't do community solar, or if we don't have the will or the numbers to do it, it'd be nice to do it somewhere in Cordova, and I'd like to try to facilitate that. We don't have the interconnect structure worked out, and it's very high on our board's radar. And we have it as one of our to-dos is to create that structure. The goal is to try to make it as painless. Basically, we want to protect the members so that the other members aren't subsidizing one member's effort. But for that member, we want to make it as painless as possible for them to use and get power back on grids. I don't know if I answered your question. I don't know of anyone we haven't connected. Potential is. But again, as a cooperative, we're value driven, so it isn't so much about the profit or necessarily just the cost. It's about trying to satisfy the membership one member at a time.
Do tidal energy?
What's that?
Tidal energy.
We had a tidal energy study done in 2000. And basically, it was a giant impoundment, like square miles of impoundment in Orca Inlet. They would fill on the tide and drain on the tide. And Orca Inlet's kind of a visible stretch of water. And building huge dikes is quite an undertaking. That technology is really advancing as well. In my little pea picking, electrical engineer brain says, if water is 200 times as dense as wind, and wind pencils out at 15 knots, then surely water can pencil out at 3, 4, 5, and 6 knots. So it's just a developing technology.
It's predictable, that's the beauty.
That's the beauty. Tidal is, unlike solar and
With
wind,
the timetable, there it is.
yeah, it's very, very predictable. It's a sine wave. So that, and you only have to store it 6 hours, right? So that reduces your storage requirements. So yeah, I'm very excited about the future of tidal.
Especially around here, I mean, it's
Yeah, we have some pretty nice little channels in there. Submarine cable, we do quite a bit of submarine cable. Very cost effective to install submarine cables. Much more so than across the land. And we've got really good luck with it. We've had 8 miles of submarine cable we've had in service for. We've had some submarine cable in service for as long as 40 years. We've had no problems.
How does increasing the impoundment of Power Creek compare to other options?
It's unfortunately Power Creek is on a huge gravel plain, and question is, I don't know. If you go way up to the head of Surprise Valley, the rock walls narrow very considerably, and there's quite a bit of the watershed. There's 25 miles total, and about I think 6 or 7 miles of it are past that point. We might be able to store some water there. The challenge with both Humpback Creek and Power Creek is they're very low elevation projects, so to get substantial energy, you have to have huge volumes of water. We run 16 billion gallons of water through Power Creek every year.
That is the upstream solutions and storage project. Is it
Yeah.
not?
But the geology is so poor, the rock's really fractured, it's a deep, that whole, the geology there is a landslide collapsed. It slid down into the basin, and that's where Omen Falls and everything is. And gravel slowly filled the whole rest of it to where there's just, the gravel's like 300 feet deep where our dam is. And that subsurface flow, the water can escape real easy. So it'd be super expensive just to explore the site. I've got a really cool 1957, I think, Department of Interior study of Power Creek Renewables. It was a 40s study. And Humpback Creek is better. Humpback Creek is a much flatter basin, and it looks to me like there's a place where there's a real narrow rock constriction, and that's a storage opportunity as well. Both of those projects are federally licensed, and that really changes the complexity and expense of evaluating. So Crater Lake is a priority over those two projects, partly because of the clean water supply. Crater Lake is also extremely clean water, much cleaner than any other water source for the community, including the Crater Creek catchment at the bottom, because it picks up organics and stuff. But the lake itself is very sterile environment. There's not, you see the flowers and everything there, but under that's a bunch of gravel and peat moss that filters that water. And the lake is crystal clear. Oh, and by the way, I took my kayak and a sonar unit and mapped the entire bottom of that lake. When we had helicopters in town down like stream gauges. Any guesses on how deep it was? Should have told one.
45 feet.
I measured 65 in one spot, and I had a plumb bob on it with a lead weight to make sure that my sonar was working right. Here's the real kicker though. At the end of July, after 2 weeks of sunshine, and remember this year all the snow was gone by the end of May, guess what the water temperature was at 40 feet of depth? Crater Lake. 62 degrees Fahrenheit. At 40 feet of depth, it was 65 degrees on the surface. So, actually, I don't think the people, scantily clad swimmers, expected a kayak to be outside of their boat. It was swimming.
What about the expense of that project if it did pan out to where it looked like? Well, first of all, you did some studies this summer on how feasible it was, and we had a pretty dry summer.
Yeah.
Is it feasible with summers like that, and how much of a cost is that impoundment going to be?
Our feasibility study is due by mid-December, and it's going to have an engineer's estimate of the cost to develop. So what they've done is they're looking at several options. So, you can try to bore a pipe through the mountain, you can install a pipeline over the surface, there's 2 or 3 routings. So they looked at several options for each element of the project, and we've pretty much narrowed it to a preferred alternative. They're going to do a cost-benefit analysis on if you get so much municipal water supply, so much energy out of it, it costs this much. Does the cost warrant the benefits warrant the cost? And then they're going to have an engineer's estimate to build it, and that estimate's going to have what they call a level 4 estimate. So it's going to range from minus 30% of their estimate to plus 50%. So if they estimate that it costs $20 million, for instance, that means it could range anywhere from 30% or $14 million to $30 million. So that kind of narrows it in and kind of gives you an idea of it. I hate to throw numbers on the table, but well north of $10 million. And it's about access and building in a remote location. And the pipeline, the actual footprint of the project will be fairly small. The dam itself maybe 30 feet wide, right, 25 feet deep. Pipeline is going to be 16-inch range probably. Power plant would easily fit in this room. And that's just because of the water element. Power plant could fit in 20 in this room.
I've been talking to canneries, and that's one reason they got to bring floaters, because There's not enough fresh water.
Water is the bottleneck. It was actually the city looking for alternative water sources that got me looking at the energy. And once I realized that it could be licensed in state and not have to follow the federal licensing process, that was. And after meeting with the Army Corps a couple of weeks ago, I'm even more encouraged. To me, the biggest barriers are cost. There's going to be some complexity between the city and Cordova Electric of who gets the water and who gets the power, because fortunately we need both pretty much at the same time almost all the time. When it's really cold and dry in the winter, our one of the river hydros shut down right as the city's reservoirs are draining out. Then in the summer when the processors are peaking, when there's a huge demand for water, is also when there's a huge demand for electricity. So we could be running it through the turbine and harvesting the energy and then letting the city take the water. But yeah, it is the bottleneck right now. The city is getting just really, they're right up against the limits of what they can do. And the existing reservoirs are not in good shape. And this one is a lot of the beautiful thing, some of the great opportunities are, there's an existing transmission line from Humpback Creek that runs right through a conventional lodge at the base of the hill. And the largest water line in the entire city is from the chlorinator building behind Orca Lodge into town, because they supersized that water line to 16 inches to allow chlorine contact time. So it's basically a big giant storage vessel. Well, if you start with much cleaner water, and then with the infrared treatment they're using, they don't have to have that chlorine contact time anymore. So they can deliver 3 or 4 times, maybe 2 to 3 times as much water through that existing pipe as they can now, without having to rebuild it or expand it. So those are two real attractive, because the delivery is often a huge part of the project cost, and those are essentially nothing for us there. So.
Are those water pipe turbines not much like Portland's doing?
You know, we've actually looked, the city asked me to look at that, and I saw that, someone sent me a link to that.
I think I did.
Yeah, and I watched that program. And we do have 2 of the existing city reservoirs we could be harvesting some electricity out of. So it's just, yeah.
And Snyder Falls, while we're on
Yeah.
kind of the hydro thing, is that?
So we're looking, we'll probably be either removing our straight gauges, which break my heart, or turning them over to others to maintain them. I think there's a great climate change study that can happen there, because there's those glaciers. The 1950s topo showed half a Snyder basin filled with glaciers. There's 2 tiny little remnants left, and I think they'll be gone in the next few years. So we've been measuring the water and the temperature. But so we got a great, I took some engineers out there and they did a fantastic, like 55-page feasibility study of that. And basically 2 years ago, they said construction cost would range between $75 and $150 million. The difference is access and no access in those 2 costs. The project is bigger than Cordova needs. So if we built a big storage project there, we would actually have more electricity hydro available than the town needs. That's good news, except that we would have to sell it all to be able to pay that huge cost for that project. So much riskier in terms of construction risk, cost risk, and whatnot than something like Crater Lake. And when you have a partner who can share the cost and share the benefit of a smaller project like Crater Lake, it's becomes really attractive. And that's the thing, if we could share the cost with the city development, then you're both developing it for less than either. But you still get basically both get the benefits.
Well, thank you so much, Clay. This has been a great presentation.